Welcome back, students. Today we're going to be doing the chain rule for the derivatives. Alright, so essentially the chain rule is we want to be able to take a derivative of a function, something like this. F of kx plus m. Right, or this is like a linear function, right, inside of a other function. But more general case, right, would be f of x, f of g of x. Right, so composition of two functions, right? G of x, now it doesn't have to be a line, right, linear function, but it can be anything. But first we're going to do intuition on essentially the line, and then we're going to move on to a general case, right? So we want to find the derivative of this, and then we want to find derivative of this, right? So that's something we have not yet encountered before. So let's go ahead and take a look at the first one, right? This is going to be number one, going to be number. All right, perfect. So for the first one, we have that, remember delta f over delta x, right? When x approaches 0. Well, we essentially can rewrite it, right, as delta f over delta, so in this case it's going to be kx plus m times delta kx plus m over delta x. Right, so those two cancel out, so we still have, right, the things we were looking for. Okay, so what would exactly be delta kxm, right? So that one would actually be, right, delta kx plus m. So that would be k times x plus delta x plus m minus kx plus m, which is equal to k delta x. Okay, if we simplify, alright, so what does that mean? That means that this is equal to delta, right, delta f over delta kx plus m, okay, times a delta x over delta x. Right, and so we know that this and this cancel out. Okay, so this part, right, we're taking a derivative, right, with respect to, so we're trading. So the whole key here, we are trading. So, you know, if we had an x, we would treat it as a x to be the variable, but now we're treating this whole thing as a variable, right? So it's just a longer way to write that variable. So we're taking a derivative with respect to this entire thing, right? Not exactly x, right? And then multiplying by the constant. So that would be f prime in general, but instead of x, we're going to write ax plus m times k. Actually, times k. All right. Okay. So essentially, right, what we got is if we want to take a derivative of f ax plus m, it's going to be first the derivative of f, and instead of x, we're going to put kx plus m inside, and then multiply by kx plus m prime. Okay, so as you can probably guess, the general chain rule will be like this, but instead of the linear function that we were able to easily prove here, that's going to be a general function g. Okay, so let's go ahead and give a definition. Give a definition of the chain rule. So the chain rule says if g is differentiable at x and f is differentiable at g of x, then the composite function capital F is equal to f composition of g, defined as f of x is equal to f of g of x, is differentiable at x and given f prime, and at x, and f prime is given by the product. So this is the formula, right, which we just showed, and we demonstrated it with the line, right, with a line. So in Leibniz notation, right, we would actually use it like this. So this is a very interesting format, right? Because we have dy over du over dx. So we did that technically right here in this step, right here in this step. This is the step that it's referencing. So this step and this step, right? This is what we did. Okay. So, and we can do essentially like this, but in the format of dy over dx. Okay. So the way we can do it is the proof of it, right, for a general function is much easier, right? Much easier. So, proof. Okay, so we know dy over dx can be rewritten as limit of delta x approaches 0 of delta y over delta x, which is equal to limit of delta x approaches 0 of delta y over delta u times delta u over delta x, right? So we can rewrite that as limit of delta x approaches 0 of delta y over delta u times limit of delta x approaches 0 of delta u over delta x. Okay, so clearly, right, we need to remember that, u goes to 0 as x goes to 0, so delta u goes to 0 as x goes to 0. So that means this is just dy over du times du over dx. And that's it. Proved. Right, and this notation is exactly what this means. Right? Same thing. So, the easiest way to get through, of course, is to solve problems. So let's go ahead and actually, before we start, I want to emphasize some of the process, right, of the chain rule. So if we're taking a chain rule, right, of a composite function, so we have to be able to identify what is the outer function, right, the outer function, and then the inner function, and then we have to take an appropriate derivative for the outer function, evaluated at the inner function, and then multiplied by the derivative of the inner function, right? So this is very, very important. So, okay, let's go ahead and take a look at the example. So we have f of x to be equal to square root of x squared plus 1. So we know that essentially, that gives us that f of u is equal to square root of u, right? And our u is equal to x squared. Okay? Or you could write it as f of gx is equal to square root of gx, which is gx is our variable, quote unquote, right? And gx is equal to x squared plus 1. So wherever notation is more convenient for you, you can use it, right? But essentially, what is the derivative of square root of u, right? We remember that. So f prime of x is going to be square root of x squared plus 1. So it's going to be derivative of this. That's going to be 1 over 2 square root of u. Okay, multiply by the derivative of this. So what the derivative of this would be? That would be, so actually, Actually, before that, let me actually write it down in color here. So we can do square root of u prime times prime. So that's going to be equal to, right, 1 over 2 square root of u times 2x. So if we substitute u, we're going to get, so 2 and 2 cancels out, right? We can note that. So 2 and 2 goes away. So what we're going to be left with is x over square root of x squared plus 1. That's it. That's our derivative, right? So it's not that scary. It's not that scary. So for example, let's digest one more example. So we want to take a look at, so part A, right? Part A is we have y equal to sine of x squared. Okay, so let's take a look at the derivative. Okay, and we will be looking at the book here. So we have that dy dx is equal to the derivative of sine of x squared. So which is sine is the outer function, right? We're defining sine to be outer function. In the previous problem, the outer function was the square root. So now the outer function is sine, evaluated, inner function is x squared, right? So now it's essentially the derivative of sine is what is cosine, evaluated the inner function at x squared, times the derivative of the inner function, 2x. So combining it together is going to be 2x cosine of x squared. Then part B, so what about y is equal to sine square x? Right, this one is a little different because now we're squaring, right? This is the same thing as sine of x squared, right? So clearly the outer function is what is outside of the parenthesis, and that's going to be the square, right? So here is a trick, right? Definitely students get tricked in that. So we essentially can write it down like this, right? We have dy dx, which is equal to d dx of sine x squared, right? So the inner function is now sine. The outer function is the square. So what's the u square? What's going to be the derivative? Is going to be 2 times u, and u is sine, right? We can view it as d dx of u squared, which is equal to 2u, right? Times, we're going to have u prime, so that's equal to 2 sine x times cosine x, where we're assuming that u is equal to sine of x. All right. So what else we can also do, of course, the power, right? We can do the power. So from this kind of problems, if we do it enough times, right, we will be able to notice the pattern. And so the pattern is the power rule combined with the chain rule. So if we have u to the power of n, it's going to be n u n minus 1 du dx. So we're multiplying by the derivative of u, so wherever is in the power. And then if we have a general g of x, is going to be just n times g of x n minus 1, which is regular power rule, times the internal part, right? The internal derivative of what we got inside. So, for example, we have y is equal to x cubed minus 1 to the power of 100. Right, our outside function is 100, right, to the power of 100. Our inside function is x cubed minus 1. So y prime is going to be equal to what? 100 times x cubed minus 1 to the power of 99 times the derivative of x cubed minus 1. So that will be equal to, so if we simplify, it's going to be 300x squared times x cubed minus 1 to the power of 9. All right, perfect, right? So of course, we can also do more complicated things, right? Such that we can differentiate by using the quotient rules or the product rule, right? Let's go through one more example here. So if we have y equal to e to the sine x, right? So our outer function is e, right? Our inner function is sine x. So y prime is going to be e to the sine x, right? The derivative of e is e, so we just leave it like this, times sine of x prime, which is equal to cosine of x times e to the sine of x. Right? That one is okay. Now, how about this example? So, by using our few previous lessons, so if we do g of t, which is equal to t minus 2 over 2t plus 1 to the power of 9, right? So here, g prime of t, so our outside function is the 9th power, so it's going to be 9 times t minus 2 over 2 plus 1 to the power of 9 minus 1, that's 8, times the derivative, t minus 2 over 2t plus 1 prime. So this is a quotient. Okay, so we're going to have 9 times t minus 2 over 2t plus 1 to the 8, times, by quotient rule, we're going to get 2t plus 1 times 1 minus 2 times t minus 2 all over 2t plus 1 squared. So if we simplify here, we will get final answer to be 45 times t minus 2 to 8 over 2t plus 1 10. Out the detailed algebra yourself. Okay, so one more formula, right, that we will be developing that formula when we move to logarithm, right? So after this lesson, the implicit differentiation will expand on the chain rule essentially, and then we're going to move to some logarithmics, right? But I'll give you this formula. Right, this formula for the exponential, right? Because we have, if b is equal to e, we are easily can have e to the x, which is e to the x, right? But other than that, we can't, right? And so, essentially, this is a useful formula, solve problems. And, you know, we probably noticed previously that if we have dy over dt is equal to dy over dx, right? Times dx over dt. So essentially, we can expand that, right? We can do as many functions as we wish. We can do dy over 2 times du dx times dx over dt, right? We can do a train of it. Times that train of derivatives helps us, right? And we will be using that for our next lesson. So let's go ahead and take a look at following. So the following example. So if we have example, we're gonna have f of x is equal to sine of cosine of tangent. Right, so essentially our outside function is sine. So f prime of x is going to be cosine of x. Oh, well, cosine, not of x, it's cosine of a cosine of tangent of x. Right, times the derivative of cosine tangent. Right, so we repeat the process. So now the outside function is cosine. So we have cosine of a cosine of tangent of x times negative sine of tangent of x times the derivative of tangent of x. Right, and last lesson, by using the quotient rule, we were able to prove, find the tangent of x derivative. So we're going to have cosine of tangent of x times sine of tangent of x times secant squared. Right, we used the chain rule here twice. Used it 2 times. All right. So, essentially, you can think about how we can prove, right, the chain rule, but we will be doing it essentially you can use the same x that we did for the linear function, regular function, right? And what we would do is essentially we would treat sketch. We would treat so u be g of x and it's differentiable, and then y is f of u, right? So it's also differentiable. So and this one is differentiable at a, and this one differentiable at b equal to g of a, right? So essentially the way we would treat the delta u would be g prime at a delta x plus some epsilon of delta x, right? Some small constant, which is the same thing as g prime at a plus epsilon 1 delta x. And then, so delta y would be f prime at b of delta u plus epsilon 2 delta u, which would be f prime of epsilon 2 of delta u. So then if we would combine the two equations and take the limit, right? So we combine the two equations, right? We will essentially end up to be delta y is equal to f prime b plus epsilon 2. So here we're going to say that epsilon is going to 0, delta u is going to 0. So we're going to get this times g prime of a plus epsilon 1 of delta x, right? And then if we divide both sides, we get that delta y over delta x is equal to f prime at b plus epsilon 2, g prime of a plus epsilon 1, right? And then we're taking limit, right? And we are limit, so if we take a limit of delta x approaches 0, right? We know that everything else approaches 0, and so this will essentially give us f prime of b times g prime a, which will end up being f prime of g of a times g prime a, and we will be done. So you can expand on the details and explain what epsilon are, but essentially that would be the end of the chain rule. All right, so next time we're going to take a look at implicit differentiation, right? And we will talk more about the chain rule. Right, see you all next time.